Hi everyone, I'm Juan, and in this video I'm going to give you an overview of the paper that Jenning, Adam, and I wrote for AISTATS 2023 on particle algorithms for fitting latent variable models to data. And I'm going to start with a problem that we deal with in the paper, which is called empirical Bayes. And in this problem we have some data y that we'd like to use to infer some unobserved or latent variables x. In order to do this, we're going to use a probabilistic model P, and by this I just mean a probability distribution jointly over the latent space and the data space that links the latent variables to the data. Now the distribution is going to be parameterized in terms of some parameters theta that we're going to have to pick in one way or another. Now throughout I'm going to make my life easy and assume that both the latent variables and the parameters take value in Euclidean spaces. Now, we approach the problem by following what's known as the empirical Bayes paradigm, which consists of first looking for some parameters, a point estimate of the parameters that explains the data well, that's consistent with what we saw according to the model. And once we have this point estimate theta star, we use it to infer the latent variables, and doing so in a Bayesian statistical sort of way, where we quantify the uncertainty in our inferences. And in other words, what we do is we produce a probability distribution over the latent space that we can use to reason about how likely we think these values of the latent variables are compared with these other ones and so on. Now what we actually do in practice is we look for parameters that maximize the marginal likelihood or the probability of observing the data that we observed according to the model. And once we found these parameters theta star, we plug them into the model and work out the corresponding posterior distribution over the latent variables, which is what we use to infer them. Now, the challenge here is the usual one. This integral is almost always intractable in the sense that we don't have closed form expressions for it, and the latent space is often high dimensional, so approximating the integral numerically is not so straightforward, and we need to work around it. Now I should point out that in some cases we're not so interested in the posterior distribution. We just like to fit our model to the data through maximum likelihood, that is, work out these parameters theta star. But even in these cases it can be helpful to take the slightly broader perspective when it comes to coming up with a solution to the problem, a way of computing these theta stars or estimating. And I hope I'll persuade you of this over the next few slides. Now, probably the best known algorithm out there for carrying out this empirical Bayes sort of approach is the EM, or expectation maximization algorithm. It does, however, have one sort of big issue. You can't actually apply it for most models out there. That's why you'd see it discussed heavily in certain specific literatures, like Gaussian mixture models, and not so much in other ones. Now, there's this interpretation of EM that I really like, and it goes back to this paper of Neil and Hinton from 20 odd years ago. Well, it actually predates this paper, but they have a very kind of nice and simple exposition of the relevant ideas. And the interpretation is as follows. It's that EM is a rather well-known optimization algorithm known as coordinate descent applied to a particular objective function called the free energy, which is this guy down here, and you can just think of it as a functional that takes in parameter values theta and probability distributions q over the latent space and spits back out real numbers. Now this issue up here that EM has is actually the same issue that coordinate descent has. It's why coordinate descent is a bit more niche of an algorithm in the optimization literature when compared with things like gradient descent and Newton's. Coordinate descent is actually not tractable for most objective functions out there. So what do people do in these cases? Well, they just throw a different optimization algorithm at the objective, hopefully one that is better suited to it. Which begs the question, could we do the same thing for the free energy? Could we just minimize it using a different optimization algorithm and so find a solution to empirical Bayes that way? And the answer is yes. People do this in variational inference all the time. There they restrict the set of all possible probability distributions over latent space to some nice tractable parametric family. In other words, some set of probability densities parameterized by some parameters phi that they call the variation parameters. They plug that into the free energy that gives them an objective in terms of both the model parameters and the variational parameters, and then they minimize that using their favorite optimization algorithm. Okay, but say you didn't want to have to pick a parametric family. Could we minimize the free energy over the space that we actually care about using an optimization algorithm other than coordinate descent? What about something like gradient descent, the first algorithm you're going to encounter if you open an undergrad textbook on optimization. So trying to answer this question is what led us to what proved to be a pretty practical algorithm that we call particle gradient descent, for the lack of a better name. Now I'm going to skip some of the technical details and just try to give you a feel for it. And I'm going to do that. I'm going to start by basically going over gradient descent for minimizing a function on Rn, on the plane actually. It's a very simple algorithm. It just says you start somewhere and you take a step in the direction of the negative gradient, or in other words, you move perpendicular to whatever contour line you started on, you update the direction of the gradient, you take another step, and you keep doing this up until you stop updating or the gradient vanishes, which means you must have reached a stationary point. Now we'd like to look for an analog of this guy that applies to the free energy, and in order to do so we're actually going to look for an analog of the continuous time counterpart of gradient descent, which is what you get by taking the step size h down to 0. In other words, updating the direction more frequently and more frequently. And what you get is this curve here moving smoothly through space, constantly following the direction of the negative gradient, and particularly constantly moving perpendicular to whatever contour line it's on right now. In this curve, it satisfies an ODE known as the gradient flow. And the link to gradient descent is that if you discretize this ODE using Eulers, you'll recover gradient descent, and the step size in the algorithm is actually the step size you'd use in the discretization. So we're going to look for an analog of gradient of the gradient flow that applies to free energy, and then we're going to discretize and approximate it until we get a tractable algorithm, something I can actually run on my computer. The analog is going to look exactly the same. It says we move in this theta and q space by constantly following the negative gradient of the free energy. And at this stage you might ask, hold on, what do you mean by the negative gradient of the free energy? We all agree what gradients of functions on Euclidean spaces are, but this is on kind of this abstract space and it's not so obvious. This question of how you define a gradient on an abstract space has actually been pretty well worked out in the optimal transport literature over the last 20 years. And it turns out that what you really need on a space to get a notion of a gradient is a metric, and once you choose that metric, this is kind of turn the crank procedure to get the expressions for the gradient, assuming a bunch of technical things work out along the way. Now, we used a gradient, a very simple metric, because it would give us a gradient flow that was easy to approximate, and the metric basically consisted of the sum of the Euclidean metric on the parameter space and the Wasserstein-2 metric on the Q component of the space, on the probability distribution component. And in that case, we would get this expression for the gradient, which had two components, a theta component that tells us how to move in thetas and how to update the parameters, and a Q component that tells us how to update the Qs. Now, if you take these expressions and you plug them into the gradient flow, you get this sort of ODE over this kind of abstract parameter cross probability distribution sort of space. Or you can also think about this as just an ODE on the parameter space and a PDE for the evolution of the densities for Q. Now, at this stage, it's useful to just stop for a second and run some sanity checks. In particular, we've defined a notion of a gradient for the free energy. What are the stationary points according to this notion? Which thetas and q make this gradient vanish? And it's pretty easy to check that theta and q make this gradient vanish if and only if theta is a stationary point of the marginal likelihood and q is the corresponding posterior. So this is good because these are the sort of points that we're actually interested in order to solve empirical Bayes. And if you work a little bit harder, you can start proving convergence of this guy here to these sorts of points. We did it in the paper for strongly log concave models, in which case you get exponential rates of convergence coming out. But I honestly think you can argue it pretty generally using something like an abstract version of Lassalle's invariant principle. But we didn't do this. Let's just say that we have good theoretical evidence to believe that this flow goes to the type of points that we're interested in. So if we could just solve it and run it for quite a while, we would get approximations to these points. Of course we can't. It's intractable for a bunch of reasons. The time axis is continuous. We still have an integral over the latent space, which is what was causing this issue from the very beginning. And on top of it, we have this kind of PDE whose domain is the latent space, which is also not a trivial thing to handle. However, it's not actually that hard to approximate and discretize this thing here to get sort of a practical set of recursions that you can actually run on your computer. And this is what they look like. There's a recursion for the parameter estimates and one for these things that we call particles. And we'll have several of these particles, capital N many. There might be 10, 100, 1,000, something like that. And these recursions are basically such that if you run them for a few steps, they approximate the gradient flow. So these guys here approximate the parameters in the gradient flow at k times h, where h is the step size that you use and k is your iteration number. And the particles are updated in such a way that if you take all of them together and you look at their empirical distribution, they approximate the q component of the gradient flow. So at the kth step, they'll approximate the q component at k times h, where h was that step size that we're using. So we know that the gradient flow goes to the type of points that we're interested, right? These stationary points of the marginal likelihood and the corresponding posteriors. If our approximations are accurate, so that these approximate inequalities hold, then we could just run this algorithm for a while that would approximate where the gradient flow went for a while, and that should be close to these points that we're interested in. And that's what we ended up calling particle gradient descent, or PGD for short. And if you look at these recursions, you'll start seeing things you recognize. This will look like an SGD sort of update for the parameters, and these guys here basically boil down to capital N sort of Euler chains that are all running in parallel. Euler chains are these things that are popular in Monte Carlo. Now, I like this algorithm because it has a sort of nice theoretical derivation that gives you some confidence that you're doing something sensible, but the reasons I really like this algorithm is that it turns out to be rather practical. First of all, it avoids accept-reject steps that show up all over a lot of Monte Carlo algorithms and are kind of finicky in high dimensions and hard to work with. If you look at these recursions, you'll see that the only thing you need to implement them is to compute gradients of the log density and add noise, and these are things you can do very efficiently using modern deep learning frameworks like PyTorch and JAX and TensorFlow and so on. The cost of the algorithm is proportional to the number of iterations you do, the number of particles you use, and the evaluation cost of the gradient. Now, the number of particle factor, you can mitigate it by just vectorizing computations across the particles. In particular, the update of one particle doesn't depend on the other ones, so it's very easy to do this. And as for the cost of the gradient, that's usually linear in the number of parameters you have, the number of latent variables, the number of data points, at least for many models out there. And if that's too expensive, maybe you have too many data points, well, you can just subsample gradients and get an unbiased estimate of them and use them that way. And everything works for the same sort of reasons as you can go from gradient descent to stochastic gradient descent. And if you're dealing with large models where things are ill-conditioned, well, we're doing an analogy of gradient descent. So we can use the tricks that we normally use for gradient descent in those cases. You can just adapt the state sizes like an AdaGrad or an RMS prop, and that will help deal with this. And for these reasons, you can actually use PGD to train fairly large latent variable models without having to use original inference. It's how these things are normally done. So here's a quick example that we did. These generator networks, which are something like a VAE but without an explicit encoder, and we were training them using PGD. In the paper, we had networks that had around 350,000 parameters and something like a couple million variables or 500,000, depending on the exact case. We were using them to generate fakes that looked like images in MNIST or images in SALAD-A, and we were doing all of this on a pretty sort of low budget setup on a Colab subscription quite quickly. And here's some pictures we would get. These are fakes for both MNIST and SALAD-A, and of course they're far from state of the art, but it wasn't bad for a low budget and kind of quick thing that we did. So thank you very much for your time.